Okay, today I will try to go on with the material. We have almost completed an example on steady, please be careful, steady motion of a body, 2D body, circular, which is symmetric, and the symmetry brings the possibility of having an analytic solution. But then we're going to do something similar, but not exactly the same. And in the second example that we're going to be analyzing this afternoon, we're going to have a disk, but this disk does not move with constant velocity. That means that it moves to the right, it moves to the left. So there is a change in velocity. Change in velocity means acceleration. That's typical of the dynamic problems. Okay, so net force, hydrodynamic force, that's what we want to calculate. And from that net force, we're going to get the concept of added mass, which is extremely important, okay, because the ship is always moving in a fluid, and it's moving with acceleration. So in the case of the ship, we always are going to have this hydrodynamic effect, okay? So that's that. And hopefully at the end of the session, we will be able to say a couple of words about waves, okay, gravitational waves. I will serve the last minutes to say a couple of words about the work that we're going to be completing next week. That means that we have to say a couple of words about teams, what are we going to do, and things like that, okay? Okay, so can you see my full screen, people?
Yes.
So this was the last part of last session, okay? We were studying this body, and the body was fixed in the space. And what we found was that with the function that we found from Newman's book, this function represents the flow, okay, like this, over a circular body, okay? If we analyze the velocity away from the body, that means that, and here there is no influence from the body because we are very, very far away, okay? In this case, this velocity is simply ui. That means that there is only velocity in the x direction, and the value is u, is constant. Close to the body, of course, we have the influence on the body, and we saw that it changes in direction, goes around the body, and then closes again, and then goes on. And if we analyze in this position, away from the body, we'll see that again, in this case, the velocity is just u, because we are away, and we cannot expect these effects to operate very far from the body. Okay, now, this was the expression that we obtained, okay, in general, okay? Let me change color, so let me write down, because I need to know more or less the dates that we are working, okay? So let me write somewhere, date here, today is what, June?
2nd.
2nd, thank you. Okay, now, let me change color, and let me say a couple of words about the expression for this velocity, okay? So I'm going to write down here the velocity v of theta on the body. See, I'm going to evaluate on R0, okay? This is the expression that we deduced, okay? So we said it's equal to minus u, this is equal to 1, so we're going to have minus 2u sine theta. So this is going to be equal to minus 2 u sine theta. Okay, now if we are here, what's the value of theta here, people? What's the value of theta here?
0.
This area would be 0, of course. Theta would be 0. Now, if theta is 0, the sine is also 0, right? That means that in the vertical direction, here, see, this is the radial, this is VR, and this is V theta. If we're about here, theta is very small, so V theta is 0, that means that this component is basically null. Makes sense, because this is symmetric body. So around here, basically the velocity is just in the x direction. There is no component in the vertical direction. Makes sense. Okay, how about here? What's the value of theta about here? Isidro, here. Theta would be
half P,
P over 2.
90.
And
Yes.
the sine of theta would be what?
Positive.
How much? Sine of 90. Sine of 90. Come on. Right away. Sine of 90.
Oh, just 1.
Yeah, a 1. So the velocity would be minus 2. So that means that this is V of theta, right? But it's equal to minus 2u. That means that this is the velocity. Make sense? Yes. It's larger than the value that we had before. And that's because when you get around the body, see, in the upper part, the fluid gets closer to each other. So the velocity increases. It goes to the right. Down here, remember, this is theta. If we go down here, in this case, how much is going to be theta? Misayo, here, theta.
3p divided by 2
And what's the sign of that?
minus
Minus 1. So the velocity in this area would be minus 2u times minus 1. So that's about 2u. That means that if we analyze in this region, the velocity will be positive. Yes, makes sense. So you see that the velocity comes like this, goes around, increases in value, and then decreases here, and then it moves to the right. Okay, so the solution makes a lot of sense. Okay, people? Okay, now, remember that V sub r is equal to 0 on the body. Why is that? Do you remember that, Ms. Astudillo? Why V sub r is equal to 0 on the body surface? Ms. Astudillo, do you remember why? The reason?
I don't remember that word.
Why the velocity has to be, the V sub r has to be 0 on the body, on the surface of the body?
Because of the radius. The same.
No. It's a physical
Condition,
characteristic.
because the
Condition
that
of
they can.
no penetration. Yes.
Yeah.
Exactly. So if you have a body, this is solid. If you have a velocity which is normal to the body, that means that the fluid goes through the surface. It makes no sense because we are saying that it is solid. So that's what we call a non-penetration condition. Okay. So the only velocity that we have on the body would be this one, V sub theta. Okay, and that will help us to calculate the pressure, which is the next step. Okay, so for the pressure on the body, we have to recall our famous linearized Bernoulli's equation. Okay. Ms. Pinkai, would you please recall me the full Bernoulli's equation? Pinkai, please. Pressure plus what? On, Ms. Pinkai, you can do it. Mr. Zamora, do you remember Bernoulli's equation? Mr. Zamora? Do you remember Bernoulli's equation?
Pressure plus velocity
One half velocity squared
divided by gravity.
Multiplied by rho. What else?
Plus the height.
Rho GZ. And plus what? Rho phi of t. And that's equal to a constant, which depends on the on time. Now, this is a steady problem. So no derivative with respect to time. We consider that Z is very large. So let's suppose that down up here, this is a free surface and we have the reference system here. So basically, rho GZ is just a constant, okay? That means that if we integrate this pressure constant on the body, we're not going to have any net value. See, so we just neglect it. So those are the two terms that we end up. And of course, the constant, okay? So what we can do is we can choose a position away, see? This is minus infinity. So here, the only velocity that we have is u. And what we can do is we can, of course, we have a pressure. We call it P sub 0 because we are way from the body. So we don't see any influence from the body. So what we can say is, okay, let's take this value simply equal to 0. And that's it. So we neglect that. And the velocity is simply equal to u. So the constant will be simply 1/2 rho u squared. Now, if we go close to the body, then, or on the surface of the body. Now here, the velocity is not u. So you see that the velocity here, it was 2u. The velocity here was 0. So we have to consider the influence of the shape of the body on the distribution of velocity on the surface. And for that, we are going to apply our equation. So we have that the pressure, the equation that we just recalled, what we do is we take this term and we move it to the right-hand side. So the pressure is going to be 1/2 rho u squared. This is simply the constant C. And this is equal to minus 1/2 rho the velocity. But we just discussed that on the surface of the body, the only velocity that we have is the tangential, because the radial is 0. Okay? Why? Because there can be, otherwise it will penetrate the body. Okay, so this is just a tangential on it. And we have that. Let me go back just a little bit here. On the body is minus 2u sine theta. So this is equal to minus 2u sine of theta. And if we replace, we have u squared here, I have u squared here, and so we can get a constant common factor, and we can put it on the denominator. This is a very common way to express this result. Okay, this is pressure, and this thing here, density, units of the density, Mr. Ramon. Units of the density, Mr. Ramon.
Mass over el longitude de Q.
And this is the velocity, so we have length over t squared. So we can cancel one of these, and this is force. So we got the correct units. Okay, so this quotient is non-dimensional. And this is that. Since this is a constant, basically this is proportional to the pressure. Okay, so let's see what happens on the body. Okay, around this area, okay, sign is 0. So basically the pressure is about 1. So we have one value here. So it's positive. Then let me change color. There. Now, around here, theta is 90, sine is 1, so we get 1 minus 4, that's minus 3, minus 3. Okay, so we got some suction. This side, on this side, theta is 180, the sine is 0, and we recuperate the value of 1. So here is plus 1. And down here is similar to the upper. So sine of 270 is minus 1, but here we have a square, so it's a plus 1. So again, we have value of minus 3. So we have positive pressure somewhere here, go to 0, and then we have something like this, like this. Like this. So this is the pressure, negative, negative. Here is positive, 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 negative. This is negative, this is positive. Ms. Vega, if you integrate this pressure over the body, what would you get according to this distribution? Ms. Vega, what would you get?
Doctor, please repeat the question.
No, I'm not going to repeat any question. No, you're not alert. I'm not going to repeat it. Mr. Iñiguez, according to this distribution, what do you expect for the force?
Which force, doctor?
In the X direction. What do you expect? Ramon, what would you say? What would you expect for the force in the X direction?
I don't know.
You see, people, you see that here you have this area, the pressure points to the left, right? Pressure points to the left. And here, this points to the right. So this cancels that one. Here, this pulls up and this pulls down. They cancel. What's the net pressure on this body, people?
0, doctor.
0.
0. This is an steady case, okay? No viscosity. We are away from the free surface, so no waves are generated. Questions about this, people? Any questions about this? No? Okay, now, in the next section, we're going to consider very similar problem, but there is going to be a large difference. And this large difference is that now the velocity is not constant. It's not a steady problem. And then the net force is not going to be zero. That's very interesting, okay? Net force is not going to be zero, okay? So that's the problem that we're going to face. So instead of explaining in detail this concept, I'm going to use an example. And from there, I'm going to explain the concept of added mass. So this is the problem that we're facing, okay? In this case, the body is moving. Let's write somewhere here. So the disk with velocity u of t. You can see immediately that u depends on time. That means that the derivative of u with respect to time is not zero. That means that there is an acceleration, okay? Now, the disk moves. That means that if I analyze the velocity here away from the body, basically it's going to be zero. Down here, away from the body, away from the body. Okay? Only in the vicinity of the body, the motion affects the fluids around it. And you can expect some velocity, some motion. But if you stay away from there, there's not going to be any motion of the fluid because you are too far away. Okay? And you can calculate this here. You can do it later. I'm not going to do it here. So you can calculate
Doctor,
yep.
you don't have the full screen.
Oh, shoot. Let me go back. Now, do I have it?
Yes, doctor.
Okay, thank you. Thank you for letting me know. Okay, so it's similar because it's a circular disk and we're going to use partially polar coordinates, but now the disk is moving and the water is static. Of course, around close to the body, there's going to be some influence, but away, no. You cannot expect, for example, if I splash here in front of Guayaquil, you cannot expect to have influence on Posora. That's the idea. Okay, we're far away that you cannot expect. But if I do my splash here on the Rio Guayas, affect what happens in Posora. That's the idea. Okay, so slightly different. But the main difference is that it depends on time. Again, we are very far away from the free surface, so we cannot expect to generate waves. There are no viscosity, and that, you have to imply that because I'm using phi. Phi is the potential velocity. Every time you use potential, that means that the fluid is potential. That means that there is no viscosity. And also, I'm not writing it here, but I can write it now. I'm writing, and that means that the density is constant. So let's go on and let's calculate now the pressure distribution, calculate the force, and let's see what happens. Now, similarly, as in the previous example, you have to, it's your responsibility to do this. You have to check that inside the domain, conservation of mass, considering that the fluid has no viscosity, is satisfied. And that's, you can do it using Laplace's equation. You have to check that. 1. 2, you have to check that there are no penetration. Okay, so here, you have to be careful because remember that the body, okay, the velocity of the body, you can calculate it using phi. But in this case, okay, the body is moving with velocity u. So in this point here, the velocity is this, because the whole body is moving with velocity u. Okay? So think about it. And finally, you have to check that away, far away from the body, there is no influence from the body. Okay? We're going to do it, you have to do it. Now let's go on and let's try to calculate the pressure distribution. Okay? So that's the problem that we're going to analyze. Before that, we recall this equation. There. So in this case, we linearize there is no influence from everybody. That means that we are very well deep away from free surface. Notice, people, notice that in the previous example, we considered the velocity. And there was an steady, so the derivative with respect to time was 0. In this case, we have to linearize because the problem is much more complex. So we said, okay, we linearize, but we keep the time dependence in our problem. Okay, it's just we simplify according to the application. In one case, we neglect that. In the other case, we neglect what we consider in the first part. Because here, we cannot include the velocity. That will give us a nonlinear term. So, and what we can do simply is saying, okay, we are going to consider that C, it's a constant pressure, right? Which integrated over the whole surface will give us no net force. So let's take the easiest value for C. So the easiest value for C is what? 0. Okay, so we take simply equal to 0. And after that, this is what we have. Before we go on, people, it's always important to check the units. The units of phi, what are the units of phi? Mr. Carrillo, what are the units of phi?
Radians.
Now?
Longitude, sorry.
What?
Longitude.
No. No. Ms. Matias, do you remember the units of phi? Matias, can you hear me? Oh, you have problems with the microphone, Ms. Matias? Ms. Matias, can you talk? No? Okay, no problem. Ms. Gutenberg, what are the units of phi? Ms. Gutenberg, what are the units of phi? No? Ms. Vega, what are the units of phi?
L square over time.
Yes, length squared over time. And since it is derivated with differentiated with respect to time, I have another time here, that's that. And of course, density is mass over length cubed. So I cancel 1. So this is force, and we have pressure. Please don't forget the negative sign. Okay, very important. Okay, let's go on. So if we need to differentiate phi with respect to time, okay, here in the expression for the solution that we have here, This is taken again from Newman's book. Okay, this is I didn't do it. It's just I just took it from Newman's. Okay. Okay. U, of course, is the velocity that changes. R sub 0 is a constant, is the radius of the disk. R and theta are the polar coordinates. Okay. Now, the thing is this: if the disk is moving, okay, in this case, we have to include a reference system, okay, whose origin is moving with the body. Okay, so if you have a point here, if this moves, that means that the distance r changes in time. Similarly with the angle, you see that this angle changes to this angle. So if we want to get the derivative with respect to time, this is what we have to have. Okay, so partial of phi with respect to u times u dt, etc. Now, you can recognize immediately that this term is equal to the acceleration. That's the key of this problem. And now we have to go on and calculate the phi dr, dr dt, the v d theta, the theta dt. Now, in general, I'm going to tell you the end of the story. These two terms are going to be neglected, but it's a good idea that you see a little bit of the handling of these terms in hydrodynamics, okay? So later on, you can talk to Professor Ruben. He's hydrodynamicist. He likes these things. Okay, so this is again the term that we were going to apply. And then what we're going to do in order to get these terms is remember that R, okay, is equal to okay, here I can define this triangle. So from here to here is x prime, and from here and up is y prime. So R is this distance is equal to that. Okay. This is the term that we are looking for. So this is what we are going to be doing. If you move in the x direction, because u is the velocity in the x direction, that means that you don't move vertically. That means that y prime doesn't change. So this term immediately is going to be 0. The one down. Let's see what happens with the others. So here, dr dx prime, so this is this one here. And here we have it. So we can differentiate partially and we get, this is what we obtain. People, you are responsible for recalling how to differentiate. The derivatives, it's something basic in engineering. What else? Dx, we need to differentiate this dx prime with respect to time. Now here, okay, if you move, you start here, you move to the right, to the left, right to the left. The final position will be the integration, here there is an integral sign here, of the velocity times dt. You integrate that and you will know the final position after some motion. By definition, because the velocity is the derivative of the position with respect to time. So the position is the integration of the velocity times time. Okay, so you know where this point, the origin, is located. And from there, if you want to signal to this point, you use r theta and relate it to x prime. Now, in this case, okay, this is what we need, which is this one. So what we consider is one fixed x point. So let's consider this point is fixed. So you move to the right, to the left, because u is not constant. Okay, so what we can do is we can differentiate this expression And since x is constant, okay, x is measured from this, and this is fixed. The system which is moving is this one, not this one. This is fixed. So x is the combination of these two is constant. So the derivative of the first term is 0. Here, this is the first theorem in calculus, remember? You're saying that the differentiation is the opposite of the integration. So you are differentiating with respect to time, and here you have the integral with respect to time. And the result is simply the integrand, u. The negative here is here. Sense? Yes, because if you move to the right, this distance reduces. If you move to the right with velocity u, this distance reduces with the rate equal to the negative of u. Makes sense. Okay, so we have all of this expression. We're going to replace in our final equation. How much is dphi du, people? How much is dphi du? Mr. Delgado, how much is dphi du?
I don't know, Doctor.
Now, we have a phi here. How much is dphi du? Miss Freire, how much is dphi du?
It's you like
Oh, no.
prima.
Right now, you are differentiated with respect to u. U is your independent variable right now. Mrs. Ro, how much is dphi du? You have to differentiate this expression with respect to this is your independent variable. Mr. Jimenez?
Sorry, Doctor. I can see.
It's like having, instead of this, let's suppose I tell you, minus x a cosine of theta. Let's suppose that this is my function of x. And I ask you, differentiate df with respect to x. What's the result of that, Mr. Carrillo?
Minus a cosine de theta.
Similarly, for this case, Mr. Carrillo, how much is dphi du? Minus
r0 squared over r multiplied cosine theta.
Yes. This is the partial differentiation, because in this case, u is your independent variable. So you have this expression for this. This is going to be considered as the acceleration, and we are going to simplify these terms. You will see that in a minute. So as a result, we get phi of t, and we replace that in the expression for the pressure. Okay? So we have everything. And before that, we are going to evaluate, we could evaluate the pressure in any point in the fluid. But of course, we are interested in the pressure on the surface of the body. So on the surface of the body, okay, since it is solid, okay, you can immediately see that if this moves to here, okay, this point with respect to this is the same as this point with respect to that. That means that on the body, dr dt and d theta dt are 0. On the body, because the body doesn't deform. Okay? So in this expression, the dr dt and d theta dt are 0. And we are left only with the first term, which is equal to du dt. Remember, in this expression, I have a negative here. This is negative, and here I have another negative. So I have two negatives that will convert into a positive. That's the result. Okay, this is the acceleration of the body, since we know that the motion is not uniform. Now let's try to draw, before we go to the break. Let's try to sketch of the distribution of pressure on the body. Okay, let's use a different color. How about green? Okay, now for this area here, okay, about this area, theta is 0. Cosine of 0 is about how much, Galarza?
1.
Cosine of 0 is about sine of 0? 1. So the pressure will be positive. So will give us that value. About here, cosine of 90, Hidrobo, cosine of 90, 0. About here, cosine of 180, minus 1. So if we take this minus 1, so instead of pushing, it will pull. That's interesting. And down here, again, is 0. So we go from positive to 0, negative 0, and then positive again. So it pushes like this, and here it pulls. Mr. Guy, just looking at this, how can you expect, what can you expect for the force on the body?
Will duplicate.
It's going to be 0 or what?
No, it's going to be the double.
No, exactly. So we're going, definitely, because just you see that the right-hand side pushes to the left, and the left-hand side, it pulls to the left. So both sides push in the one direction. Yes, we're going to integrate that, and we're going to obtain a net force pointing to the left. Okay, so there's going to be a net force. This is the force that we expect to the left. I'm writing this as a small f because there is an error in your class notes. Please correct, because this is a 2D problem. When we use 2D problems, we calculate forces per unit length. Okay, every time we use per unit something, we use little letters. When you use full force, use full moment, we use capital letters. So this should be little f. Okay. So we're going to obtain a net force pointing to the left. People, is there any viscosity? No, this is ideal fluid. Is there any effect from the pressure, from the static pressure? No, we consider this basically uniform. What's the origin of this net force? The acceleration. So from now on, every time you consider the motion of a body with acceleration, even in the cases of potential flows, you are going to have a net force on the body. Even if you consider no viscosity, no wave generation, every time you oscillate, you are going to have a net force, hydrodynamic force. See, the previous example, it was an steady case. The rest of the conditions were the same. Net force, 0. In this case, the only difference is now the velocity is not constant. It's not steady, changes in time. The result, you have a force, net force. And if we are working in dynamics, ship dynamics, the ship is not moving like this. The ship is moving like this. So up, down, up, down. So you change in velocity. Acceleration, then you will have a net force, even if you consider that the fluid were ideal. Let's take a break. And when we return, we're going to integrate this pressure. We're going to get the force per unit length, and the result you will see there will be the definition of what we call added mass. Isaac, would you please stop the recording